In mathematical physics, the WKB approximation or WKB method is a method for finding approximate solutions to linear differential equations with spatially varying coefficients. It is typically used for a semiclassical calculation in quantum mechanics in which the wave function is recast as an exponential function, semiclassically expanded, and then either the amplitude or the phase is taken to be slowly changing. The name is an initialism for Wenzel-Kramer's Brillouin. It is also known as the LG or Liouville-Green method. Other often used letter combinations include JWKB and WKBJ, where the J stands for Jeffreys. Brief history. This method is named after physicists Wenzel, Kramers, and Brillouin, who all developed it in 1926. In 1923, mathematician Harold Jeffreys had developed a general method of approximating solutions to linear, second-order differential equations, which includes the Schrödinger equation. Even though the Schrödinger equation was developed 2 years later, Wenzel, Kramers, and Brillouin were apparently unaware of this earlier work, so Jeffreys is often neglected credit. Early texts in quantum mechanics contain any number of combinations of their initials, including WBK, BWK, WKBJ, JWKB and BWKJ. Earlier references to the method are Carlini in 1817, Liouville in 1837, Green in 1837, Rayleigh in 1912 and Gans in 1915. Liouville and Green may be said to have founded the method in 1837, and it is also commonly referred to as the Liouville-Green or LG method. The important contribution of Jeffreys, Wenzel, Kramers and Brillouin to the method was the inclusion of the treatment of turning points, connecting the evanescent and oscillatory solutions at either side of the turning point. For example, this may occur in the Schrödinger equation, due to a potential energy Hill WKB method. Generally, WKB theory is a method for approximating the solution of a differential equation whose highest derivative is multiplied by a small parameter epsilon. The method of approximation is as follows. For a differential equation, assume a solution of the form of an asymptotic series expansion in the limit delta 0. The asymptotic scaling of delta in terms of epsilon will be determined by the equation. See the example below. Substituting the above ansatz into the differential equation and cancelling out the exponential terms allows one to solve for an arbitrary number of terms Sn in the expansion. WKB theory is a special case of multiple scale analysis. An example. This example comes from the text of Bender and Orsic referenced. Consider the second-order homogeneous linear differential equation where, substituting results in the equation to leading order, the above can be approximated as in the limit delta 0. The dominant balance is given by so delta is proportional to epsilon. Setting them equal and comparing powers yields which can be recognized as the aconal equation, with solution considering first-order powers of epsilon fixes. This is the unidimensional transport equation, having the solution where k1 is an arbitrary constant. We now have a pair of approximations to the system. The first-order WKB approximation will be a linear combination of the two. Higher-order terms can be obtained by looking at equations for higher powers of delta, explicitly, for n2. Precision of the asymptotic series. The asymptotic series for Y is usually a divergent series, whose general term delta nsn starts to increase after a certain value n equals nmax. Therefore, the smallest error achieved by the WKB method is at best of the order of the last included term. For the equation with q less than 0 an analytic function, the value and the magnitude of the last term can be estimated as follows. Whereas the point at which needs to be evaluated and is the turning point where, closest to, The number nmax can be interpreted as the number of oscillations between and the closest turning point. If is a slowly changing function, the number nmax will be large, and the minimum error of the asymptotic series will be exponentially small. Application to the Schrödinger equation. The above example may be applied specifically to the one-dimensional, time-independent Schrödinger equation, which can be rewritten as the wave function can be rewritten as the exponential of another function phi, which could be complex, so that where phi indicates the derivative of phi with respect to x, this derivative phi can be separated into real and imaginary parts by introducing the real functions a and b. The amplitude of the wave function is then, while the phases, the real and imaginary parts of the Schrödinger equation, then become next. The semiclassical approximation is used. This means that each function is expanded as a power series in H. From the above equations, it can be seen that the power series must start with at least an order of 1 h to satisfy the real part of the equation. In order to achieve a good classical limit, it is necessary to start with as high a power of Planck's constant h as possible. To the zeroth order in this expansion, the conditions on a and b can be written. The first derivatives a and b were discarded, because they include factors of order 1 h higher than the dominant h minus 2. Then, if the amplitude varies sufficiently slowly as compared to the phase, finding the next order of the expansion yields, as in the example of the previous section. It is evident in the denominator that both of these approximate solutions become singular near the classical turning point, where E equals V, and cannot be valid. These are the approximate solutions away from the potential hill and beneath the potential hill. Away from the potential hill, the particle acts similarly to a free wave. The wave function is oscillating. Beneath the potential hill, the particle undergoes exponential changes in amplitude. To complete the derivation, the approximate solutions must be found everywhere and their coefficients matched to make a global approximate solution. The approximate solution near the classical turning point C equals V is yet to be found. For a classical turning point x1 and close to E equals V, the term can be expanded in a power series to first order. One finds this differential equation is known as the area equation, and the solution may be written in terms of area functions. This solution should connect the far away and beneath solutions, given the two coefficients on one side of the classical turning point. The two coefficients on the other side of the classical turning point can be determined by using this local solution to connect them. Thus, a relationship between them can be found. Fortunately, the area functions will asymptote into sine, cosine and exponential functions in the proper limits. The relationship can be found to be as follows. Now the global solutions can be constructed. For an estimate of the errors in this approximation, see Chapter 15 of Hall.